Hey, what's going on guys? Tanmay here for Simple Snippets, and in this video tutorial, we are going to understand insertion in a binary search tree using recursion. So if you've been following this data structures and algorithms playlist, this course on this channel, we have already implemented pretty much all the binary search tree operations, both theory as well as the practical side. And in practicals, we've seen the C++ program to implement the entire binary search tree and the different operations. However, this one topic was left out where we had to do the insertion using recursive method. So on the screen right now, what you're seeing, that is insert node, is the pseudocode for insertion using iterative method. So there is no recursion used over here. So some of you had asked me how to do the insertion using recursive method. So in this tutorial, we will see the entire working of recursion and how insertion works in binary search tree using recursive functions. We will not only dry run the pseudocode of the insertion using recursion and see the diagrammatic working, but also at the end of this tutorial, we will see the C++ code, that is we will convert the recursive insertion pseudocode to a C++ code and see the working. Okay. This is a very important topic guys, because this concept will also be used in AVL tree. So make sure you watch this video till the end. And with that being said, let's get started. Okay, so as you can see on the screen, this is the entire pseudocode for binary search tree insertion using recursive function or recursion. Now before we proceed, I'm assuming that you guys have already seen the other videos on binary search tree, or you already have good idea about what is binary search tree, how insertion works, at least theoretically the working. And I'm also assuming that you guys already know the concept of pointers, the concept of recursion, the concept of object-oriented programming, that is objects and classes, etc, etc. If not, I have separate tutorials on all these topics on our channel. Some of them are in the C++ beginners course, some of them are in this DSA course. Please make sure you go through them thoroughly, because only then you'll understand this very properly. And this video might be a little lengthy, but please bear with me and watch this video in one stretch with full concentration. Only then I can assure you that it will be very easy to understand. Okay? Alright. So starting off, this is the function name that we are going to give, insert recursive. You can also keep it plain and simple insert. The return type of this function is a pointer of tree node type or tree node class. So tree node is nothing but our user defined class, and you can see it on the screen. So this tree node class has a left tree node pointer, a right tree node pointer, and the center one is the value. So this is how a structure of a typical node in a binary search tree looks like. We've given the class name as tree node. You can also give it node. It will have a left pointer, which will also be the type of tree node. It will have a right pointer, which again will be type of tree node, and the center one is an integer value where we will actually store the value. So this value is also sometimes called as key or data. Okay. Alright. So the reason why it is going to return a tree node pointer is because it is a recursive function, and you'll see the working later on. So moving on to the arguments, it has two arguments. Both of them are of tree node star type, which means that both of them are accepting pointers of tree node. The first argument, that is the first argument, is going to be the node that you are at currently, because you're going to traverse to the end of the binary search tree and then insert at the end, right? So this R is going to represent that current node that you are at, and this second pointer, that is star new node, is going to be the new node obviously that you want to insert, hence the name new node. Okay, makes sense? Now as you go inside this pseudocode, inside this function, there are four major parts. So the first part, that is point number 1 or statement number 1, deals with an empty tree or a tree where you've reached the end. Okay, so in that case the R value is going to be null, and don't worry, I'm just going through the pseudocode right now and it will not make much sense as of now, but once we start to dry run this code, that is dry run this pseudocode and see the diagram, everything will be very easy. So right now I'm just quickly going through the steps. So the first step, as I mentioned, is related to the empty tree or the point where you reach the end of the binary search tree, that is the leaf node. In that case R is going to be null, and in that case we will say R equals to new node. So attach or transfer the address inside the new node into the current node. So new node and R both are pointers, they will have addresses, correct? So that is what we are doing over here, transferring the address of new node into the current node, and then you will say return R. The reason why we are saying return R is because obviously we have a return type. Okay. So the second condition is when the new node's value, you can see new node value, and the reason why we are using a hyphen and then a closing angular bracket is because new node is a pointer, and the way we access data members in an object which is pointed by a pointer is using this operator and not the dot operator. The dot operator is used when we have direct object. So we have obj.datamember. But when a pointer is pointing to that object and you are accessing data members or member functions of an object using pointer, then you have to use this syntax. Okay. So over here in second condition, we are checking if the new node's value is less than the current pointer's value. So you can see is less than is the condition. If it is less than that, then we have to do recursion on the left side. So you say r of left equals to insert recursive. We are passing the left child's address over here and the new node again. So insert recursive is nothing but a recursive call. You can see if new node's value is less than the current node, recursion on the left. So this is where first recursion happens. The third condition as guessed is if the new node's value is greater than the r value. In that case, you will do recursion on the right. So r of right and r of right are passed. If new node's value is greater than the current node, recursion on the right subtree. And the last one or the last condition is when new node's value is equal to the current node's value, and that state is not allowed because our binary search tree we are designing or making it such a way that we are not going to allow duplicate values. So in that case, we will simply print no duplicates allowed and return the current r value. And once all of these things are done, lastly we have simply return r, that is return the current r value where we are at, because we need to return something from this function. Alright, now reading through this entire pseudocode I know made no sense as of now. So now let's actually try to dry run this code with the help of diagrams and with the help of addresses and proper structures. Okay, so in the main function, that is when we write the code, in the main function what we will do, we will create an object of binary search tree class. So BST is nothing but another class that we have defined, inside which we have one single data member which is a root pointer of type tree node. And then this binary search tree class will have all these functions. Okay, so this tree node insert recursive is another function that is going to be a member function of this BST class. So whenever we call insert recursive, we will use this object and we will say obj.insert recursive. Alright, so that's why we have to first create this object. When you create this object for the first time in the memory, let's say this is the RAM, in the memory what will happen? This object will be created and this star root data member will also be created. Initially, since there is nothing inside this, it will have null, right? So this star root pointer is pointing to null initially. Let me write null over here. Okay. So initially you can see this object is created in the memory in the RAM. It will have this pointer of type tree node root and it will have null inside because it is not pointing to anything as of now. Alright. So this is the first thing that we do in the main function. The next thing that we do is we create an object. Using this syntax, we say tree node star new node. So this new node is nothing but a pointer and it will point to the object in the heap memory. Okay, so this syntax basically creates an object in the heap memory. Let's say this is the heap memory and the address is #77. This is where the object is created and the object is of course of tree node type because we are saying tree node star new node. And this new node, as I mentioned, is a pointer. So this new node may be somewhere over here. Let's say this is new node. New underscore node. Okay, it is a pointer. It is a pointer of type tree node and it is going to point to this object in the heap memory. So this #77 will be stored in this new node pointer. Okay, so this line or this statement has this effect inside the memory. So the reason why we did this is because we wanted to create this node in the heap memory because it will have global scope. And that will be used when we are creating the entire binary search tree. So now what we have is we have a new node pointer which is there in the stack memory. Let's say there is a divider over here. This is the stack memory and this is the heap memory. The heap memory is related or associated with the dynamic memory allocation side. And in stack we have static memory allocation. Please look up this topic if you don't know. I have discussed dynamic memory allocation separately as well. But yeah, right now what we have is we have an object in the heap memory at address location #77. That address is stored inside this new node pointer which is pointing to that object. Okay. Alright. At this step we say new node value, which means that the value inside this node, we will take it from the user. So let's assume we are taking 56. Okay. I've already written 56 but initially it will be blank. But let's assume that we are taking val from the user and storing it over here. Okay. And the last thing is, now we will give a call to this insert recursive function using this object itself, which is the binary search tree object. We will say obj.root. Now the reason why we are saying obj.root is because this insert recursive function is going to return us a pointer of type tree node. So on the LHS also we need a pointer of tree node type, and that is exactly what this root is. This root is nothing but a data member inside this obj object, remember that. So it's also a pointer of tree node type, so that can be taken as LHS. And to the RHS we have this insert recursive function, and inside that we are passing this root node itself. So initially, of course, when you create the obj object, the root is going to be null. You can see over here, this object is created in the memory. We are passing null. So first we are passing null. The second parameter is this new node itself. So now we are passing this new node over here. So this new node will be passed as it is. Okay. Both of them are pointers. So this new node will be passed as it is, that is as a pointer. Okay. And now this is how the function call will look like. So the first call looks something like this. obj.root equals to obj.ir. IR stands for insert recursive. I have written it in short. The first argument R, right? So this is the first argument R. So the first argument is for the root node, correct? obj.root. So now one more pointer R will be created in the stack memory. Let's name it R. And this is a local variable inside the function, right? It will be only live inside the function. And this obj.root value null will now be copied in this R value also. So R will also have null because it is also a pointer of type tree node, right? So R is nothing but null initially. Alright. Comma new node. So new node is going to be passed as it is. So let's say one more pointer, which is a local pointer or local variable which will be alive or live only inside this function, which is again new node. Let's name it new node only. And it will have the address #77 because we are passing new node. So this will have #77. Okay. Now these two are the local variables which will be alive only inside the first function call. So they will only have the scope inside this insert recursive function. Okay. Alright. Now let's start off with step number 1. So at step number 1, we are checking if R equals to null. We just said R is equal to null. So R value is also null, which means that the first condition itself has become true. So now we will go inside the if, we will say R equals to new node. So what is the value inside new node? New node is nothing but a pointer of tree node, correct? It has the value #77. So #77 will be now transferred into R. R is also a pointer of type tree node, you can see over here. So both of them are compatible. So now R will store #77. So R will have #77. Okay. Now after this we have 1.2, we will say return R. So when we say return R, this function will stop working because a return statement will basically come outside the function, and we are saying return R. R has #77. So from this function, R with the value of #77 will now be returned, and since obj.r is on the RHS, it will be returned to the LHS. What is there to the LHS to catch that value? We have obj.root. So obj.root was null, but now R has been returned with the value of #77. So now this root will now have #77. Okay. Alright, so let's erase this and write #77 over here. Now once we do that, in the memory also, now you can see that the root pointer inside the object has also now started pointing to this node created in the heap memory. Correct? Alright. So our first value is basically inserted using this function. Okay. So far we've still not used the concept of recursion. That is because this was our very first node to be inserted into the binary search tree. Now let's insert one more value. Okay. So now let's try to insert a new node with the value 35, right? So again, we will create this new node. So the binary search tree object we will create only once, okay? This will be created only once. These steps will be happening multiple times, and for that we will write a loop, okay, which will keep on running. So we will create a menu driven program. So again, a tree node object will be created in the memory. So let's create that. Let's say it is created over here. Let's say it has the address of hash 90, correct? Let's say it has the value, what do we have the value? 35. Alright. So again we will give a function call. We will say obj.root. So again this is the first function call. We will say obj.root equals to obj.insertRecursive. We will pass the root node. We will pass obj.root. This time obj.root has a value hash 77, correct? So this pointer R will be created in the stack. So this is a local pointer which will be only alive inside this insert recursive function. So the scope will be limited to this insert recursive function, and this R will be equal to obj.root. What is there inside the root of the BST object? It is hash 77. So hash 77 will be stored inside R, right? So R will have hash 77. Okay. Now we have created this new node pointer again. So new node will be there in the stack. It is a pointer which is having hash 90. So it is pointing to the actual node created in the heap memory. So this is that node, and it is pointed by this star new node value or star new node pointer. Okay. So now new node will be passed basically the address which is hash 90 this time. Okay. Now let's start off with the first statement inside the insert recursive function. So the first statement we check if r equals to null. Now this time r is not null because r is having hash 77, which means that r is actually pointing to some value. So r has hash 77 as the address, which means r is also pointing to the very first node, right? So the first node was created at the memory address hash 77. The second node that we want to insert is created at the address of hash 90, correct? Now these are all fake addresses. We are just using them for reference purpose, right? So r is pointing to the first node right now, which means r is not null. So the first condition is not true. We will proceed with the second condition. In second condition, now we are checking if new node's value, what is the value of new node? New node right now, which is also passed over here, is basically another new node which is gonna store hash 90. So this new node is separate, or it is a local variable which is also basically going to point to the same node. Okay. So it is pointing to this object with the address hash 90 and it has the value 35. So here we are checking is 35 less than r of value. R is pointing to hash 77 which is 56, who has the value 56. So is 35 less than 56? Yes. So this time we go inside this second condition and we execute step number 2.1, and now we are saying r of left equals to insert recursive. So now we are going to do recursion on the left side, correct? So r of left, r is pointing to the first node 56. Let's name it n1 just for our reference. So r of left is nothing but the left pointer it has, and of course it doesn't have anything to the left, which means that it will have null. So r of left, that is this second function call, r of left equals to, again insert recursive r of left. R of left is nothing but null over here. So we are passing null over here, comma, this same new node. So another local variable will be created in the stack. Let's say it is created over here. Okay. And this will also have the same address hash 90 and it will also point to the same object. And the reason why we have multiple creations is because now we are going function inside function, kind of like a inception, right? So this new node is different from this new node. These are only local variables which are alive or which have the scope inside the function. So just understand that we are passing the same node, that is the address of the same node. So hash 90 is passed. So when you give the second recursive call, so this is the second call, correct? The first call will go in a pause state at step number 2.1. So over here, let's draw a pause symbol at step number 2.1. So the first function gave a call to second insert recursive function over here, correct? At step number 2.1. So the first function obviously will go in a pause state, and now we will start with the execution of the insert recursive from the start for the second call. So in the second call, again we will go in step number 1, we will check if r equals to null. And now this time you can see that this r is equal to null. That is what we've passed over here. You can see null. That is because it was the left pointer of n1. n1's left pointer has nothing, so it means that it is null. So the first step is true. So now we will say r equals to new node. What is r over here? R is null and r is nothing but this left pointer of n1. So we've passed the left pointer of n1 and now we are saying r equals to new node. New node we've passed hash 90. So now we will say r equals to hash 90. So hash 90 will now be stored in r. R, as I mentioned, is nothing but the left pointer of n1. So now over here we will have hash 90. Correct? So basically what we did is we linked the first node n1, let's name this one as n2, with n2. So we linked n1 with n2 and n2 became the left child of n1. Alright, and once you do that we will say return r. So now what is r? R we just said is hash 90 at step number 1.1. So hash 90 will be returned. Hash 90 will be returned and stored as r of left. This r of left is nothing but n1's left. So that's why you can see hash 90 is now stored over here. Okay. So I hope you're getting this recursion. I know it is a bit cluttered and it is getting a little messy over here also in the diagram. But I hope you've understood how we assigned hash 90 as the left of the first node using recursion. So once we say return, the second recursive call is done and now you can go back to the calling function. You'll go back over here and now 2.1 will resume. So first function call, that is first obj.ir, will resume after 2.1, and after 2.1, since 2 was executed, 3 will not be executed, 4 will not be executed because this is if, else if and else control statement. So if one of the condition is executed, other two will not. So we are remained with return r. So for the first function, r is nothing but the root. So 77 will be stored and saved in the root. So 77 will be restored as it is. Okay. Alright. So far what we've done is we've inserted 2 nodes and let's try to insert one more node for better understanding. Let's say you want to insert the value 40. Okay. So you've created one more node in the heap memory. Let's create that. Let's say the value is 40. Let's say the address that it is created at is hash 12. Okay. Now you want to insert, you can see this is the node over here. We still have to do the insertion. So 40 you have to insert or attach in this binary search tree structure. Alright. So the first thing that you have to do is you'll say obj.root. obj.root. You'll say insert recursive and you'll pass the root node. So the root node has hash 77, right? So over here the r value is going to be hash 77, comma, the new node that is supposed to be passed is hash 12. Correct? These two values are passed over here in the first function call, that is first insert recursive call. So you'll go inside, you'll check if r equals to null. No, r is not null. We just said r is equal to hash 77. So you can see the root is pointing to the very first node. This is nothing but n1. This is nothing but n2. And this is nothing but n3 that we want to insert. So we've given these alias names. These are not real names. This is just for our reference. Alright. So first statement is not true. R is not null. So we will proceed. Now we will check if new node value, so the value of 40 is less than the value that we are currently pointing. R is currently hash 77. It is pointing to n1. The value is 56. Is the new node value, which is 40, less than 56? Yes, it's true. So now you will go inside and now you will call r of left. So a second function call will be given. Correct? From the first function call over here, the first function will go in a pause state at step number 2.1. And now you're saying r of left. So you're passing n1's left, right? R is currently 77, which means r is n1. What is there to the left of n1? It is hash 90. That is the left pointer of n1. It is hash 90. So you're passing hash 90 as the new r. So for the second function call, R is nothing but hash 90, comma, new node. So new node is passed as it is, which is hash 12. That is the address of this new node that you want to insert. Okay, let's say it is created at an address of hash 12. Alright, it's still not linked over here, right? Okay, so now that the second function call, that is second insert recursive, is called, let's start its execution. The first step is if R equals to null. For the second recursive call, which is over here, R is hash 90. So hash 90 is not null. So step number 1, not true. We will proceed. Now over here we will check if new node, the new node value is hash 12, which is 40. So 40, is it less than R of value? Is it less than R of value? R is currently 90 inside the second recursive call. Hash 90 is nothing but N2. N2's value is 35. Is 40 less than 35? No. This time the second statement is also false. That is, this condition is also false. So now we proceed with the third statement. In the third statement, we check if this new node of value, which is 40, is it greater than R of value? R of value we just said is 35. So is 40 greater than 35? Yes. So now this time we have to go to the right of N2. So now we will say R of right. R is hash 90 in the second recursive call. So now we are giving a third recursive call. You can see R of right. So we will say R of right, which is nothing but blank over here. So R is hash 90 for the second recursive call. So hash 90 is nothing but N2. And when you say R of right, it means N2's right. N2's right is blank. So that is what is there on the LHS. So whatever this recursive call will return, it will be stored as the right address of N2. Correct? So on the RHS, we have this recursive call insert recursive. We will again say R of right. R of right just now we said is null. So we will pass null over here, comma, new node. So this new node is passed as it is. That is the address which is hash 12. Okay? Because these are pointers, right? So now for the third recursive call, we've given a third recursive call. So second will go in a pause state. So second will go in a pause state at step number 3.1. And now we've given a third call. That is a second recursive call. So first was a regular function call. The second was the first recursive call. The third was the second recursive call. Okay? Alright. Now let's start off with execution of the third function call. In the third function call, the first step or the first statement is if R equals to null. So this time we've passed null, right? So R equals to null in the third call, and new node is nothing but hash 12, which is as it is. That is the address of this node N3. This is node N3 that we are assuming. Let's say it is N3. Okay. So now this condition has become true because R is equal to null. That is what we've passed. So now we will say R equals to new node. So R equals to new node. New node's address is hash 12, right? So hash 12 will be now stored in R. And after that we have return R. So hash 12 will be returned to the R of right of N2. Correct? Because on the left hand side we have R of right for N2. So that would be stored over here, which means that hash 12 will be now stored as the right address or right pointer. So basically we've returned from the third function call back again, and in that we have basically linked N2 and N3. You can see N3's address is hash 12. N2's right pointer is now hash 12. So we have linked this, and over here also in the memory diagram, N2's right should have hash 12. N1's left should have hash 90, right? Hash 90 over here. So N1 is linked to N2, N2 is linked to N3. In the memory also, this is how the linking will happen. So once we come back, the second recursive call, which was paused at 3.1, will resume. Correct? So we've returned. So this is where it was paused. That is the second recursive call. You can see 3.1. So after 3.1, we have only one step, return R. So for second recursive call, what is the value of R? R is hash 90. So hash 90 will be returned back, and it will be stored as R of left of N1. So for N1, what is R? Hash 77. So N1's left is hash 90. So 90 will be again copied over here, so that linking is maintained. And then you'll again come back. So when you'll come back, so first insert recursive function was paused at step number 2.1, which is over here. So after that we will also say return R. So for the first function, what is the value of R? R is 77. So 77 will be again stored in obj.root. So again hash 77 will be maintained as it is. So when you go back, the original addresses will be restored. Okay, they would be recopied, but they would be copied as same. So backtracking, we will have the similar addresses. Only when you are giving the recursive calls, you will proceed depending upon whether the value is small or greater. Okay. Alright, so now you can see that we have basically created a binary search tree with 3 nodes. And the reason why it is a binary search tree, because it is following the principle that for a particular node, the left child has to be smaller and the right child has to be greater for every node, right? So you can see over here, for n1 the left child is n2 having the value 35. For n2 the right child is 40, so 40 is greater than 35. Okay, so now what you can do is you can pause this screen and you can yourself add a few more nodes by dry running this pseudocode and going back again, doing all the diagrammatic rough work to understand the entire recursion. I hope this entire working is now clear to you guys. Now let's jump to the last part where we convert this insert recursive pseudocode, this entire steps, into proper C++ code to see its working. Okay, so as you can see, I have already written quite a lot of code, and this is something that I will be sharing with you. So in the video description, you can check out this entire code on our official website. I highly recommend that you type it at least once. If you followed this entire playlist, and if you've seen the previous tutorials, I'm guessing you guys already have quite a lot of code already, and we've already implemented BST entirely. So there will be only one extra thing that you have to add, which is this insert recursive function. So on the top, this is the class tree node. Then we have the class BST. Inside that, this is the iterative insert node. You can see there is a lot of code. And below that is where we have insert recursive. So this is that function. I'll show you the pseudocode on the right. Correct. So this is the first condition. This is the second one. This is the third, fourth, and the last return call. Right. Below that we have a print 2D function which will simply print the entire tree in a 2D way. It will be rotated in a 90 degrees fashion, which I will show you in a minute. It is just to see how the tree is created. And in the main function, you can see we create the object. We ask the user to, input the option value that he wants to do. Let's say he wants to insert, he will insert 1. If he wants to search, he will input 2. Right now we are dealing with only insert, so we will input 1. And this is inside a do while loop, so it will keep on executing till we enter 0. Okay, so this is a menu driven program. Then we will take the value from the user. So first we will take the option number that the user wants to do. Of course we will insert 1 only in this case. We will create this new node. Then in the switch case, it will always be case 1 in this tutorial because we are dealing with insert. We will ask the user to enter the value of the tree node to insert in the binary search tree. So user will insert the val. Then you will assign the val inside the value data member of the object which is pointed by this new node which we created over here. And lastly, we will give this function called insert recursive. You can also test the regular iterative insert node function. I have commented it over here. Let's save this and let's go to execute, compile and run. I'm not typing it because again it will be a waste of time. You guys can get the entire code. We just want to see whether it is working or not. So this is how the menu driven program will look like. You will say option number 1. You'll enter the value 55, hit enter. The value is inserted. Basically, I have not shown a message. You guys can print a message saying value inserted. Again, option 1, let's insert 24, hit enter. Again, option 1, let's insert 87. Hit enter, and now let's enter option 4, which is for printing the binary search tree values. When you hit enter, you can see print 2D function is called, and this is the tree. So 55 is the root node, 34 is the left child, and 87 is the right child. So you can see the tree is a little rotated, but this is the best way you can represent a tree in a structural way onto a command prompt. Okay. So our code is working perfectly fine. We are inserting values in a recursive way, and we have successfully implemented insertion in a binary search tree using recursion. Okay, so I'm going to wrap up this video over here. I hope you've understood the entire concept of insertion in a binary search tree using recursive functions or recursion. This was one topic that was left. In further videos, this concept will also be required in AVL tree. So again, if you have any confusions, go back and check out the entire pseudocode, dry run it, take a pencil and paper and dry run the entire pseudocode step by step, and I'm pretty sure things will be very clear. Okay, so I'm gonna wrap up this video over here. Please give this video a like if you've understood the entire concept. Definitely let me know in the comments how this video was. Do share it with your friends. This is a very important topic, and I'll see you guys in the next one. Peace.